Hello, everybody, and welcome to another talk in the Astro3D ECR Astronomers in Australia seminar series. My name is Dr. Amelia Fraser-McKelvey. I'm a postdoc at the University of Western Australia, which is part of ICRA, and my co-chair today is Dr. Dorota Bayer, who is at Swinburne University of Technology. So before we begin today, it's important for us to acknowledge the traditional custodians of the land on which we meet today. So the Aboriginal and Torres Strait Islander people were Australia's first astronomers, and we acknowledge their long-standing systems of knowledge on which we continue to build today. We acknowledge the traditional custodians of the unceded lands on which we are meeting today. So myself and our second speaker today are speaking to you from the land of the Whadjuk Noongar people. My co-chair Dorota is joining us from the land of the Wurundjeri people of the Kulin Nation. And our first speaker today, Simon Murphy, is speaking to you from the land of the Gadigal people of the Eora Nation. We pay our respects to their elders past and present and extend that respect to all First Peoples joining us here today. So why are we here? This series is facilitated by Astro3D, which is the ARC Centre of Excellence for All Sky Astrophysics in 3 dimensions. It's a bit of a mouthful. COVID-19 has affected our ability to travel and present at international seminars this year, especially for us in Australia. The time zones mean that often meetings that take place at 2 or 3 a.m. in the morning pass. This lack of opportunity to network could disadvantage junior astronomers when entering the job market. This series aims to combat these issues by providing a platform for junior Australian astronomers to present their work to the world. So thank you, World, for coming. A little bit of housekeeping. We've got 2 talks over this hour. The first, each will be 20 minutes in length with 5 minutes for question time. Please save your questions until the end of the talk, and you can feel free to either pop them in the chat function, which Dorota will read out, or you can raise your hand and ask it yourself. These talks are being recorded and they're going to be placed afterwards on the Astro3D YouTube channel for educational purposes only. So by being here today, you're agreeing to abide by Astro3D's meeting code of conduct. Okay, so let's move on to our first speaker then. So our first speaker is Dr. Simon Murphy, who is a postdoc at the University of Sydney. Simon will be talking to us about a pre-main sequence star that's chemically peculiar due to its planet-forming disk. So Simon, you can go ahead and take it away. Thank you.
Thanks, Amelia, for that introduction. And thanks, everyone, for tuning in. Indeed, today I'll be talking about this young star that's chemically peculiar due to its planet-forming disk. And I'll start off with a bit of an overview about how we know that. So the star's name is HD 139614, and it lies in Upper Centaurus Lupus, which is part of the wider SCO-SEN association. And what I have here is an age map of SCO-SEN. And this has been derived using about 500 stars. What you can see is basically position on the sky, and the color indicates age. So blue is younger stars and red is older stars, but in broad terms, these are still very young stars with ages between about sort of 5 and 30 megayears. HD 139614 lies at this purple circle almost in the center here. And from the association age map, we get about 14 megayears, but with a pretty sizable uncertainty. So one thing that's quite common in these stellar associations is something called age gradients. And that's where the age of the region basically depends on the position on the sky. So you can see that in the top left of the map, you've got the younger stars. And as you go towards the lower right, the ages tend towards older stars. But we also have this thing called age dispersion, which basically means that that's not a very smooth age gradient, and you get sort of clumpy areas where the age is quite different, such as that patch of dark red in the lower right of Upper Centaurus Lupus. And it's these that give us pretty large uncertainties on our ages, which are in this case about 30% uncertainty. Whereas astroseismically, that is using the stellar pulsations, we've been able to determine the age of this particular star to much higher precision, to about 10% precision. So from our modeling, we get an age of 10.7 megayears, which indicates that this star is on the pre-main sequence. It's very young. The star is also chemically peculiar. It belongs to this class called the Lambda Boo stars, and they're characterized by basically solar abundances of volatile elements, so carbon, nitrogen, oxygen, but deficiencies in iron peak elements. And so from spectroscopy, we get an abundance for iron that's minus 0.6, which translates to a metal mass fraction of about 0.004. Whereas with our astroseismic modeling, we infer a metallicity of 0.01, so a considerably larger metal mass fraction. And that confirms that this star is chemically peculiar. And then that last major property is this planet-forming disk. So HD 139614 has this warped disk with ring structures and cavities in it. So the polarized scattered light image on the left shows the warp because the inner ring is illuminated on the left side as we're looking at it, whereas the outer disk is illuminated on the right side as we're looking at it. And the right panel of that plot shows these rings and these arcs that are basically a key feature of this disk. And the figure on the right is a model of that disk, and it has a pretty large gap at a few AU, and that's indicative of these cavities that I mentioned. And what's happening here is as the embedded planets orbiting within this disk, they're basically sucking up all of the dust, but not all of the gas, which leads to these peculiarities that I'll explain a little bit more towards the end of the talk. So when I say we've measured the mass and we've measured the metal, what I mostly mean is astroseismically. And in case you haven't heard about astroseismology before, I'll just give you a little overview of how this works. The idea is that many stars are driven to oscillate at their natural frequencies. And what we observe are several, we call them modes of pulsation. So you can have something that goes straight through the star or sort of skirts around the edge. These are different modes of pulsation, and each mode has a different period. And that period depends on, well, it's the time it takes for that mode to travel through the star, but that depends on the internal density profile of the star, which could mean, for instance, the star is very centrally condensed. So it might be an old star where you've had a lot of core burning, or the star could be relatively homogeneous. It could be a large star, which means a long travel time. It could be a small star. So all these things dictate the mode frequencies, and those mode frequencies are something that we can quite easily measure. So mode frequencies are essentially the fundamental data of astroseismology. HD 139614 was observed for a whole month at 2-minute cadence by the TESS satellite. That's the Transiting Exoplanet Survey satellite. And if we take the Fourier transform of that TESS light curve, we see all of these peaks in the bottom panel. And each one of these peaks represents a pulsation mode within the star, and the frequency of that mode can be inverted to get the mode's period. So they all contain a lot of information about what's happening inside the star. Now, I don't want you to focus on the meanings of the circles and the triangles at the moment, only to say that we see a pretty regular spacing of peaks at high frequency in this star. So the triangles on the right-hand side are all separated by about the same amount, which is the interval between these dashed lines. And we call this interval delta nu. This is the astroseismic large spacing, and it scales as the square root of the mean stellar density. So what that means is if you have a very low density star, you'll have a very small delta nu. However, for this star, delta nu is pretty high, which means the star is very dense, and that's consistent with our observations of it being very close to the zero-age main sequence. I would also point out that this regular spacing of modes for delta Scuti stars is a very new thing. This was published in a paper in Nature last year, led by Tim Bedding at the University of Sydney. And we found 60 or so of these delta Scuti stars with this regular spacing. And so we know that 6.83 cycles per day, which is the value for this star, is a pretty large value and indicating that the star is pretty dense and pretty young. So when we carry out these astroseismic analyses, we use a tool called the Échelle diagram. Échelle is the French word for ladder, and that's to do with how we process the spectrum. The amplitude spectrum. I'll just restart. No, I won't restart this GIF. I'll just restart the slide apparently. Okay, so I'll talk you through how we construct this diagram. We start off with the Fourier transform that you saw on the previous slide, except this is a different star. But we divide it up by that regular spacing delta nu that we saw earlier, and we stack these slices. Then we encode the amplitude information in those slices in grayscale, and that forms the Echelle diagram. So I'll just talk you through that one more time. We take our Fourier transform, we slice it up into those regular slices of size delta nu, and then we encode all of the amplitude information of those peaks as grayscale. So darker color means stronger amplitude, and that forms our Echelle diagram. So here's how we make that Echelle diagram for this particular star. We choose the value of delta nu. That makes ridges in this diagram appear vertical. And as I said before, that value happens to be 6.83 cycles per day. And at high frequency, we had these little red triangles that were on the left side of each of our slices. So when you construct the Echelle diagram, you see a ridge on the left-hand side where you have one peak in each slice going upwards. And the blue circles are the other peaks that are identified, and they form a ridge that comes down the center. And what we know from our study of 60 or so stars in that Nature paper is that that ridge curves towards the lower right. Now, this allows us to do something really important, which is identify the modes. So by comparing to models, we found that peaks on the left side of the diagram happen to be L equals 1. So here L is the spherical harmonic that's analogous to the spherical harmonics in quantum mechanics. So these L equals 1 modes are what we call dipole modes, and they happen to be on the left side of the diagram. Whereas that curved ridge down the center describes the radial modes. So they're the modes that you get when the star is just pulsating in and out. Mode identification was previously intractable for Delta Scuti stars, which basically meant that we would observe the star, we would know that all of these peaks were found in the Fourier transform of the light curve, but we had no idea which particular modes they were, and therefore we were very limited on the information that we could gather about the internal structure of the star. But now we can identify several modes in the same star, and that really allows us to constrain the interior, which basically means the mass, metallicity, and age that we need to know to be able to characterize these protoplanetary disks. And the way that we do this modeling is by chi-squared minimization. So what that means is we construct models. In fact, we constructed 100,000 models for this particular star, and we construct pulsation frequencies for those models. And those model frequencies are shown as open symbols on this diagram. And then we compare them against the observed mode frequencies, which are the red symbols. And then you basically calculate the difference for each matched mode, that's hard to say. And what you're looking for is a low chi-squared, so a small frequency difference summed up across all of the modes that we observe. When you do this, you have to be very careful that you've got the correct mode ID. If you identify a mode incorrectly, you're going to throw off the analysis. So to sort of secure against that, what we did is constructed 10 different mode ID scenarios basically for this star. And then we ran all of them just to make sure that we found the global minimum and that any uncertainty in the mode identification was accounted for. And an important thing that comes out of this is that strong peaks are not necessarily in, by which I mean, in this particular slice on the Echelle diagram, we've got this pretty strong peak, but in none of our models did this peak correspond to one of the dipole modes. So you have to be really careful that you account for, or at least allow for, uncertainties in mode identification when you're doing this modeling. So here's how we went about this modeling. We started off with an HR diagram like this in the top right, and we constructed many evolutionary tracks with a code called MESA and corresponding pulsation frequencies in a code called Jaya. So we start off with the classical error box. So this is the observed temperature and luminosity with the uncertainties, and that gives you this green box in this diagram. And we calculated tracks that were roughly solar in metallicity and that had ages younger than 30 megayears, because we know from the stellar association that this star is not going to be older than that. And what we do is we evaluate the mass on the x-axis, metallicity on the y-axis of all of these models. And we sort of start to build up a grid in this mass metallicity space. And we evaluate the chi-squared looking for regions of low chi-squared. But each star or each point on this diagram doesn't represent only one model, because for every model, there are dozens of ages that were evaluated, and we evaluated other sort of internal parameters for the star, such as the efficiency of convection. And what we found is in the center of this diagram, well, at least as you see it now, we had a global minimum in chi-squared, but the search was adaptive. So if we found an area of low chi-squared, then we calculated more models surrounding that area to make sure that we found the global minimum. So we ended up with these 10 to the 5 different models, and they're shown in this corner plot here. So what you're looking at in gray is every single one of those 10 to the 5 models that we calculated. And then in color, using this color bar here, we're showing all of the points with chi-squared less than 1. So these are our best fitting models. And then in red, we have a convex hull for the classical error box, meaning that any points that are inside the red box have both low chi-squared and they're consistent with the observed temperature and luminosity of the star. And the results from this are that we get about a 1% precision on mass, a 10% precision on metallicity, and a 7% precision on age. And this is really unprecedented for this type of star. And it's really because we were able to identify so many of these pulsation modes. And it also helps to have modes of different degrees because they penetrate to different depths within the star, making them more sensitive to, for instance, the stellar age and how metallicity changes as a function of depth in the star. One thing that we found was that there was no dependence on alpha MLT, this mixing length parameter. So that's in this panel here, and we basically get no dependence from the left side to the right on this parameter. So it's not a particularly important parameter in the pulsation modeling of this star. So why chi-squared equals 1? Why did we choose that as our threshold? On the left here, what you're looking at is a simple scatter plot of one of the parameters, the metal mass fraction, and how the seismic chi-squared statistic depends on that. And what you see is we have this fairly broad minimum in chi-squared in a certain range of metallicity. But then we also have this sort of extra dip, which is what we call the global minimum in chi-squared. And that just happens to lie below 1, even when the observations, the observational uncertainties on the frequencies are arbitrarily set to be the same for every single mode. We didn't apply any extra weights for any particular modes. We didn't renormalize the chi-squared in any way, and we still end up with this neat little dip just below 1. Very convenient. And then we determine our final parameters using only those models that are in the global chi-squared minimum. What I'm also showing in this diagram are blue points and gray points. So the blue points have classical agreement, meaning they're consistent with the observed temperature and luminosity, and the gray points don't. So actually this global minimum is a bit better separated from the rest of these points than the gray dots here would indicate. So how are we able to get,
Simon?
Okay, thank you. So how are we able to get such precise values for these quantities, the mass, the metallicity, and so on? Well, it turns out that in this part of the HR diagram, for these pre-main sequence stars, the pulsation properties change extremely rapidly with age. So on the left here, you're seeing that same plot that I showed earlier. That's the HR diagram with the evolutionary tracks. And every track in that diagram has identical properties except for small differences in mass. And then for those same tracks on the right 2 panels, we'll start with the bottom one. We're looking at the core carbon-12 abundance as a function of age. So what happens here is the star comes down towards the 0 age main sequence, and then it starts CNO burning. So it starts burning hydrogen via the CNO cycle. And so the carbon-12 content in the core plummets in a very short span, in a sort of 2 mega years, really. And at the same time, the pulsation frequencies are changing very rapidly too. This is that astroseismic large spacing that I mentioned earlier. That's changing very quickly with age too. So the frequencies are essentially super sensitive in this particular age range, allowing us to get these precise results. Excuse me. I would also add at this point that we didn't include rotation in our modeling. We sort of left that for future work, but we did account for it in our uncertainties. So we made our uncertainties bigger because we didn't include rotation specifically. And we also didn't yet look at accretion, but that's going to be quite important for this star in future work that we're doing. So I'll just give you a quick summary of what I've said so far. So HD 139614 is this young star still on the pre-main sequence, and we derive this pretty precise astroseismic age. And we also know that it's chemically peculiar. It's one of these lambda Boötis stars, And we observed that the global metal abundance is close to solar, whereas the spectroscopic abundance, which represents only the surface, showed that it's much more metal weak than this. And that's indicative of that chemical peculiarity. And then HD 139614 has this planet-forming disk. It's warped, it has ring structures, it has cavities, and that's indicative of these embedded planets that are still forming and trapping dust within the disk, causing the chemical peculiarity. Because these planets, they're shepherding this disk material, they're not allowing the dust to accrete onto the star. So the refractory elements, the ones that are found in dust, essentially get incorporated into planets rather than accreting onto the star. So the star is depleted in refractories like iron peak elements. Whereas the gas is free to accrete onto the star. So volatile elements like carbon, nitrogen, oxygen, those end up being pretty solar in abundance because there's nothing inhibiting them particularly from accreting onto the star. So this was an observational confirmation of the theory by Michael Kammer. And we're doing more work on this star, as I said, where we're going to model rotation and model accretion specifically in order to get some basically more precise inferences on the disk as well as the star. How am I doing for time, Amelia?
Just about done.
Just about done. Okay. Then allow me just to make a quick final word on astroseismic ages if I have a minute. So of all the things that we can measure for stars, ages are notoriously difficult. We can measure parallaxes, velocities, we can take spectroscopic measurements and so on. And these all translate to intrinsic properties of stars in a sort of indirect way. So the mass, the metallicity, the age, the rotation rate, these are all properties of the star that are somewhat difficult to disentangle in a lot of circumstances. And astroseismic ages can be really good for this. While we have empirical age indicators like gyrochronology, these only work for certain types of stars. So there's this relationship between stellar activity, so sort of flares and star spots, and stellar rotation and stellar age. This only really works for sun-like stars. It definitely doesn't work for early type stars, so A-type stars like Delta Scuti stars. Instead, we need a different method. And what most people fall back on is stellar isochrones. These are a model-based inference on stellar age. But for isochrones, metallicity is a problem because isochrones of different metallicities end up overlapping. It's quite hard, again, to disentangle the difference between mass, metallicity, and age. But astroseismology can get through that problem. And you don't need an ensemble of stars like you need for isochrones. You're not hindered by dust in the same way because extinction isn't a problem, reddening isn't a problem. So astroseismic ages are looking like they can make some really solid inroads to the ages of stellar associations where other techniques have only been able to get sort of 30% uncertainties. And that's it from me. Thank you very much.
Thank you very much, Simon. Great talk. I'll hand over to Dorota for question time.
Yes, thank you, Simon, for this great talk. Do we have any questions from the audience? Please raise your hand or write a question in the chat.
Hi, Simon. Nice talk. Early on in your slides, you showed the spectroscopic metallicity compared with the astroseismic one. Why is there such a big difference? It seemed like there was a big difference anyway.
Yeah, that's right. So the spectroscopy is really only sampling the very surface layer of the star, the photosphere of the star. Whereas the astroseismic metallicity is sensitive to the interior because the modes are penetrating deep within the star, especially these radial modes that travel really throughout the entire star. And so what you're seeing is that the photosphere is representative of this material that's recently accreted from the protoplanetary disk, and that's sort of enhanced in these volatiles and really depleted in the refractories, whereas the bulk composition of the star is material that was assembled much earlier in the star formation process. So that's more indicative of the overall metallicity of the star and of the disk. And that's pretty cool because we have very few ways of precisely measuring the composition of the disk. And that's why we're so excited about modeling this star in more detail, also accounting for accretion and perhaps even doing a two-zone model of the star where you have a zone that's affected by recent accretion and a deeper zone that is not affected by recent accretion.
So just to explore that a little bit more, if there's no other questions. No. So you say the spectroscopic metallicity is probing the surface essentially, and what has recently fallen onto the star.
Yep.
And you're saying that perhaps the disk is actually holding many of the iron peak elements.
Yeah, specifically those refractory elements, so those elements like the iron peak elements that are readily incorporated into dust. They also are readily incorporated into planets, whereas the gas is much harder to accrete onto planets, so it's a lot freer within that disk, and essentially free to accrete onto the surface of the star in a way that the refractories are not.
So is there enough mass of these elements in the disk to account for the underabundances seen in the star?
That is a really good question, because that depends on the current accretion rate, the length of time that accretion has been going on for, and also how efficient the mixing processes are in the star. So for instance, how deep is your surface convection zone that will mix the surface layers and drag that accreted material deeper into the star and then back up again. And so this is all stuff that we're hoping to model once we account for accretion in our future astroseismic modeling. Thanks for the question.
Okay, thank you.
Okay, we have another question from Tanda.
Hey, great talk, Simon. Thank you. Just two quick questions about your pulse spectrum. Can you back to your pulse spectrum?
Yeah.
Yeah. So first question is the dashed line doesn't overlap with the peaks. Is there any particular reason that you plot in this way, or you just want to separate the peaks and dashed line? And so the second, the second question is, so this is a star close to zero-age mass sequence. So I guess it should rotate very fast. But in your comparison between the model and the observation, I didn't see obvious rotation effect. Do you have? Can you give it more context about that? About rotation?
Okay. So two things to unpack. So the first one is the easy one. The why the dashed lines don't fall on the peaks. So the dashed lines are just integer multiples of delta nu calculated from 0. This is just the way that it's done. It's the way that shell diagrams are made. Ultimately, it doesn't really matter whether you start at 0 or if you choose it to align on the peaks. But if you did choose delta nu, if you did basically put these dashed lines on the peaks, and that's where your shell orders start, it means that every peak falls at the edge of the diagram. And so if you get a slight deviation in the regular spacing, then the peak suddenly jumps to the side of the diagram. And that's super difficult to interpret. So it's just convention that we start at 0. The other question about rotation was great, actually. So if I show you the shell diagram here, there were lots of peaks that we essentially extracted. So, I mean, you can see them in the Fourier transform. They're up here, for instance, where we don't have a symbol above it because we haven't identified that mode. And so those include strong peaks like this one in the shell diagram that don't fall within our pattern. And so what happens when a star rotates is that the frequencies of some of the pulsation modes end up shifted to different frequency values. And if you don't account for rotation, you get a lot of frequencies that fall directly on top of each other. But when you do account for rotation, your model frequencies will be split by that rotation frequency. And so a lot of these, let's call them unidentified peaks, are the result of rotational splitting. And we've started modeling that rotation already, and we are able to identify rotationally split multiplets. And what that means is that we're able to measure the internal rotation rate of the star as distinct from the surface rotation rate of the star. So you can also probe differential rotation throughout the star with astroseismology. So that's pretty cool. And another thing is that the spectroscopy combined with the imaging of the disk tells us that this star is seen close to pole on. So by having measured V sin I, the spectroscopic surface rotation velocity, and knowing the disk inclination, we actually know how fast the star is rotating. And so we can compare that measurement with what we measure from astroseismology and basically confirm that we're getting it all right as well.
Cool, thank you.
All right. I think it's time to move to the next speaker.
Okay, thank you.
Yes, let's
Thank-
thank Simon again for a very interesting talk. Thank you very much, Simon.